So today's topic is phase lag compensator design. And when we look at a phase lag compensator, the transfer function is going to remain the same. So here we have GC of S, which is again a compensator or a controller transfer function, and its transfer function is 1 plus Ts divided by 1 plus alpha Ts. In the phase lead compensator, alpha was between 0 and 1. Okay, it is, and in this phase lag compensator, it is going to be larger than 1. Okay, so in this case, the corner frequencies will shift their places. They will be swapped actually. Okay, and here T is still a positive quantity, and we would like to look at this phase lag compensator, and we would like to benefit from it in a control loop. So here, I will look at the frequency response of this thing, GC of j omega, 1 plus j omega t, and 1 plus j omega alpha t. And when I look at the corner frequencies, I have 1 over t as the corner frequency of the numerator, and the corner frequency of the denominator is 1 over alpha t. Remember, if alpha was between 0 and 1, then this corner frequency was greater in that case. Okay? Now alpha is larger than 1, meaning that this is going to be smaller. Okay? So I have 1 over alpha t corner frequency. It is smaller than 1 over t. That means that when I look at the magnitude of this thing, from the low frequencies, I will first hit the corner frequency of the denominator, and then I will hit the corner frequency of the numerator. Okay, when I look at the frequency response, that is going to change in that manner. This is omega, and I can here try to plot the phase waveform. So here, if I mark the corner frequencies, I will have 1 over alpha t here and 1 over t here. I have 10 over t, and I have also 0.1 over alpha t. I have the same frequencies here, 10 over t, 0.1 over alpha t. Okay? So now maybe I should put these up so that because the frequency response is going to go downwards here, so I can maybe write them above the values here. So I have 1 over alpha t, 1 over t, 10 over t, and 0.1 over alpha t. So when I look at the magnitude in dB scale, then when omega is very, very small, in that case this GC of j omega is going to be 1. Okay, approximately. And in that case, I see that until I fit the smaller corner frequency, the magnitude is going to be 0 dB. Okay? And afterwards, we are going to hit the corner frequency of the denominator, which is actually going to decrease the phase. Because if omega reaches that value, I see that in that case, this is going to start becoming important. And this term is going to be, when the frequency is between these corner frequencies, the numerator is still 1. Okay, because we still have not reached the corner frequency here. So this one is 1 there in this interval, and this one is looking like this. So here, the transfer function that I have to draw the magnitude for is 1 over j omega alpha t approximately in this interval. But that is going to be, when I increase the frequency 10 times, that magnitude is going to decrease by 20 dB, meaning that I'm going to have a minus 20 dB per decade slope here. And finally, then we are going to hit the corner frequency of this numerator, and in that case, this is negligible. This one, the denominator is going to behave like this around there, and the numerator is going to behave like that. So the transfer function is going to be looking like this. And in that case, I see that j omegas are actually cancelling. It's going to be a constant gain in that case. Okay? So that actually means that I have a constant. So it doesn't look like a constant in my perfect drawing here, but it is going to be a constant there. Okay? And what is this magnitude at which we saturate? In dB, in linear scale, what is it? Let omega go to infinity there. it is going to be 1 over alpha. So I will take its dB magnitude. It is 20 log 1 over alpha. So we see that 1 over alpha is a number smaller than 1, meaning that its logarithm is negative. That is why this thing is here. Or I can write minus 20 log alpha. That is the same thing. Okay? So now let us look at the phase. If omega is very small, in that case this is going to behave like 1. Okay? Meaning that it doesn't have any phase. So we have 0 phase here, and we know that if omega is very large, these j omegas are going to cancel, and this is going to be again a constant positive gain. So the phase is approximately 0 for large frequencies as well. In between, first I'm going to hit the corner frequency of the denominator. That actually means that the phase is going to start becoming negative, because for these frequencies we have the numerator approximately equal to 1, but the phase of this thing is going to start increasing. Okay, and when the phase of the denominator increases, we get a negative decreasing phase. Okay, so this is going to start decreasing here, and at some point it's going to make a minimum, and then we are going to reach this. The phase of this thing, numerator, is going to start affecting the result, and it's going to be reducing the phase back to almost 0. Okay? This is the frequency response of a phase lag compensator, and it is exactly the reverse of or the negative of the phase lead compensator. In phase lead compensator, we used phase in order to be able to increase the phase margin of the system, and the magnitude was a side effect. Okay? In the phase lag compensator, the jobs are going to change. Okay? So we are going to use the magnitude of this thing to increase the phase margin of the system, and then phase is going to be something which is going to act as a side effect in phase lag compensator design. So here's what we're going to do. So let's say that this is my magnitude, and let us say that this is my phase, and that is minus 180 degrees. So let me start somewhere like this. So here, this is the angle, and this is the magnitude here. So for such a system, combining these two things, how can it be useful? So here is what is going to happen. So without the combination, when I combine these, magnitudes are going to be added, and the phases are going to be added in the open loop. And when I look at the closed loop systems, then I'm going to determine, for example, if this compensator is not in the open loop, I can look at what the phase margin of the system is. So this is the gain crossover frequency, and I can read the phase margin here. Okay? So let us say that this is approximately at minus 180 degrees, meaning that the phase margin of the closed loop with only this open loop transfer function is going to be approximately 0 degrees. So suppose that I would like to increase the phase margin to 30 degrees, or let me say 50 degrees. One idea is to use the phase lead compensator. Lead compensator would increase this phase, and it would increase the gain crossover frequency slightly. But if I want to use the lag compensator for the same purpose, how can I use this thing? So here I see that if instead of increasing the gain, if I can decrease the gain crossover frequency is going to shift to the left. Okay? When the gain crossover frequency of the system shifts to the left, when I decrease the gain, I see that the phase of the system would automatically increase. And this distance between minus 180 and the phase of the system at the gain crossover frequency is going to increase. So suppose that I would like to increase the phase to 30 degree phase margin. So suppose that this is the point minus 150. Okay? So then I'm going to try to do the following. I would like my new gain crossover frequency at this point. Okay? So if I want my new gain crossover frequency at this point, so to make the phase margin 30 degrees, I will want my new gain crossover frequency at this frequency. So in order to be able to do that, what should I do? in order to be able to have this frequency as my new gain crossover frequency, what should I do? To have this point, to have this frequency as my new gain crossover frequency instead of this, what should I do to the gain? I need to decrease the gain. How much should I decrease it? I need to look at the gain here of the system itself, and I need to decrease it this much. Okay? I'm going to get that decrease from the phase lag compensator, negative gain here. Okay? So I will equate 20 log 1 over alpha to the gain of the system at the required gain crossover frequency. Okay? So I will want 20 log 1 over alpha to cancel this positive gain here. Okay? I will, in some way, I will reduce this gain to come to here so that my new phase margin is actually 30 degrees. Okay? Then what is going to happen to this phase? Because this negative phase is going to come as a side effect of the compensator. Okay? That is going to try, if I place this frequency somewhere around here, this phase is going to pull my phase further down. That is why usually we will try to put this transfer function to as much left as possible. Okay, so we are going to place this thing somewhere around here so that this phase decrease does not affect us. But we would still get the gain decrease here, which we are going to benefit from. Okay, that is how we're going to design a phase lag compensator. Any questions here? So now, what do we mean by design? Again, we have the similar block diagram. So I have a K. I will put the compensator here, GC of S, and I will have an original system G of S. Okay, that is my overall system. So I have here my G of S, and in the example that we are going to solve, we will have G of S given as 2 over S plus 1. We have already seen this example. G of S is going to be something whose transfer function we will know. We are considering the analytical design in this case. Okay, so the transfer function of G of S is given to us. When it is not given to us, we will get only the body plot of G of S, and based on that body plot, we can make a graphical design only, okay, without extracting any transfer function from the body plot. Instead of this, if we can get the body plot of G of S, then we can design the same thing without knowing the transfer function of the system. And designing means that we need to find K, we need to find alpha, we need to find T, to satisfy some performance requirements. There are usually two performance requirements to be satisfied. The first performance requirement is related to the steady state. The second performance requirement is going to be related to the transient, which is going to be related to the phase margin. Okay? In the example that we are going to solve, we are going to say that the steady state error should be less than 0.1 to unit step input. Sorry, unit ramp input. And phase margin should be larger than or equal to, in the example, it is going to be 35 degrees. Okay? So this ensures that steady state performance is fine. This ensures that the transient performance that we are going to get is fine. So now that is how the design problem is specified. Now we are actually ready to go over the steps of the design. Actually, the first 3 steps are going to be the same as phase lead compensator design. Completely the same. But I'm going to repeat it so that you again try to see the whole procedure. So step 1. Find K to satisfy the steady state requirement. In this case, we have a steady state error requirement to unit ramp. Okay? So we have, therefore, E steady state is going to be 1 over kV. Okay? And we want E steady state smaller than or equal to 0.1. So what is the smallest value of k, or the largest value of kV that we have to use here? 10. So here kV should be 10, and we know that kV is limit as s goes to 0 s times the open loop transfer function. Okay, this is limit as s goes to 0. Open loop transfer function is k gc of s and g of s. K gc of s and g of s. When I look at the compensator here, when I let s go to 0 here, the compensator is going to be 1. Okay, so it is not going to change the steady state performance. So I really do not have to consider gc of s there. So here, when I take this limit with that g of s transfer function, what is going to be the limit?
There is an s, right?
Yes, of course, there is an s here. When I take the limit, what is going to be the limit? Substitute g of s, multiply it with s, and I will have 2k here. Take the limit, what do we get? It is just going to be 2k. This means that k is going to be 5. Okay? So we have found already one of the parameters of interest. Step 2 is going to be to combine k and g of s. The combined system is going to be called the uncompensated system. Okay? So this is going to be called g uncompensated of s, or in my notes you might see it as g combined of s. It is the same thing. G uncompensated of s is going to be k times g of s. Okay, so that is going to be 10 over s plus 1. Okay, this is the uncompensated system, or uncompensated open loop system, I can actually say. So this is so without g of s, we have this closed loop transfer function, and I can try to understand what the properties of this uncompensated system. And now, after the combination, step 3 involves to draw the body plot of g uncompensated of s. Okay. So far everything that I have done is the same as the phasing compensator design. Okay. So now let us try to look at the body plot of g uncompensated of s. So this is my magnitude plot, and this is going to be my phase plot. So I have g uncompensated magnitude in dB here, and here is the angle. So here I will look at the frequency response of this thing. That means that I will substitute s equals to j omega here. This is going to be 10 over j omega 1 plus j omega. Here, sometimes the transfer functions really are not in body form, so bringing it into body form first and then trying to draw the body plot might be more useful. But this is already in body plot, in body form. That is why I can substitute directly s equals to j omega here. And in this case, if I look at the corner frequencies, there is only one corner frequency, which is 1 radians per second. Okay? So let me say that this corner frequency is here, 1 radian per second, and I will have 10 radians and 0.1 radians per second here. Okay? So now let me look at the magnitude at low frequencies. If we are at a frequency which is at least 10 times smaller than the corner frequencies here, so if we are at frequency 0.1, then this one is going to be negligible. J omega here will be negligible if we are at a smaller frequency than the corner frequency, which is 1. So for frequency 0.1, this transfer function is going to be looking like 10 over j omega. And the magnitude of that thing is 10 over omega. If I would like to draw this thing in dB scale, what should it look like in dB domain? It's going to be a line with a slope what? Minus 20 dB per decade. Okay? So here, if I increase the frequency 10 times, the magnitude is going to decrease 10 times. And 10 times in dB scale would mean minus 20 dB. Okay? Because 20 log 10 is just 20. Okay? So here I will draw a line with minus 20 dB per decade slope. but I need also a starting point. The starting point is going to be obtained at the frequency 0.1. If I substitute omega is equal to 0.1 here, the magnitude is going to be 100 in linear scale. In dB scale, it's going to be 40 dB, meaning that if I put 40 dB here, we're going to start this plot somewhere here. And I'm going to draw a line with minus 20 dB per decade slope. So the frequency increases 10 times from 0.1 to 1, meaning that the magnitude is going to decrease by 20 dB here, and it's going to come to 20 dB at the frequency 1. Okay? And when we pass the corner frequency 1, then I'm going to start neglecting this 1 here. Okay? If frequency is above 1, then I'm going to neglect this 1. And then the magnitude is going to be looking like 10 over omega squared. I have double j omegas here, meaning that I will have 10 over omega squared. And when I look at this thing, it is going to be again a line, but its slope is going to be minus 40 dB per decade, meaning that when the frequency increases 10 times, the magnitude decreases by 40 dB. Okay? So I have minus 20 dB here, meaning that I'm going to come here at the end when the frequency increases 10 times. So this is what the magnitude plot is going to be looking like. And when I look at the phase plot, I have 10 and I have 0.1 here. Phase is going to start at low frequencies from where? If omega is very small, this transfer function is looking like 10 over j omega. What is the phase of 10 over j omega? A single j would bring us 90 degrees. Since it's in the denominator, it's going to bring us minus 90 degrees. So for low frequencies, the phase is at minus 90 degrees. Okay? So it's going to start from here. For large frequencies, where is the phase? For large frequencies, this thing is going to be looking like 10 over j omega squared. Okay, for large frequencies. Each one of the j omegas will bring minus 90 degrees, meaning that the phase as omega goes to infinity is going to be minus 180 degrees. So for large frequencies, the phase is going to be almost at minus 180 degrees. Okay? And what is going to be the phase at the corner frequency exactly? Minus 135. Because here at the corner frequency, this is going to be 1 plus j, which has 45 degree phase. Okay? Meaning that this is going to bring me minus 90, and this is going to bring me minus 45, meaning that the overall phase is going to be minus 135. Okay? So right in the middle here is going to be my phase. And if I try to connect these parts, I'm going to get a phase waveform, which is looking like this. As I told you over and over, this is the same thing that I have done already for phase lead compensator design. Now the steps are going to start differing from phase lead compensator. So now let me say step 4. Find the new gain crossover frequency. Omega GC. Okay? So here is what we are going to do. I need to actually find here. I have minus 135 here. So currently the phase margin is looking like this. So I have a small phase margin, and currently it's not going to be sufficient for us. Okay? So in the last lecture we have calculated that this distance was 17 degrees. So currently the phase margin of the closed loop without the compensator, it is 17 degrees. Okay? This is the phase margin of the closed loop system. We are drawing the body plot of the open loop system, and based on the open loop system, we are determining the phase margin of the closed loop system. Okay, that is what we are doing here. And this phase margin is actually really small currently. It is at around 17 degrees. But by using the gain reduction of the phase lag compensator, we are going to reduce the gain so that at the new gain crossover frequency we have a larger phase for the system and we will have a larger phase margin. Okay? If I want 35-degree phase margin, where should this phase cross? At which point do we need our new gain crossover frequency? So here, where should I look at G uncompensated of J omega GC? This should be minus 180. I will add a 35 here, okay? But here, as I told you, I will try to push this transfer function to as much left as possible, but I will not let it go to minus infinity on this plot. Okay? So here, there might still remain a tiny phase, negative phase, that is going to be added by this phase lag compensator phase. That is why we usually add just a 5 degree of error margin here. Okay? So then what is going to be important for us is going to be the point where the phase crosses minus 140. Okay? I will check where this phase crosses minus 140 here. Okay? So I'm going to look at this point and I will try to make the new gain crossover frequency exactly this point by reducing the gain of the system by using the phase lag compensator. How can I find this frequency at which phase is equal to this? I'm going to just look at the phase of this thing. What is this phase? The phase of this thing is minus 90 degrees coming from the j omega term. And from this term, what should I write? The phase of this thing is the arctangent omega. Okay? And this is going to bring me minus arctangent omega GC. Okay? This is the phase of this thing, and I want to find the frequency where this phase is equal to minus 140 degrees. Minus 140 degrees. Okay? This is going to make the arctangent of omega GC equal to 50 degrees, and omega GC is going to be the tangent 50 degrees. Okay? If you look at this tangent, you're going to see that it is going to be 1.2 radians per second. Okay? It's just going to do this. So the new gain crossover frequency is going to be where the phase of the open loop system without the compensator crosses minus 140. It is going to be somewhere here. Okay? So now let us look at step 5. Find alpha to make omega GC the new gain crossover frequency. So here G uncompensated of J omega, which belongs to that body plot, is 10 over J omega 1 plus J omega. And what I have to do is that I need to make this point my new gain crossover frequency. So I see that, then what should be the magnitude of the combination of these two systems at this frequency? The combination of G uncompensated and the combination of the compensator, the magnitude of the combination has to be what there? It has to be 1 in linear scale, so it has to be 0 dB. Okay? So here, the magnitude of the uncompensated system at that point is G uncompensated of J omega GC. Okay? This is the magnitude of the uncompensated system only at that point. And we are looking at it's a positive number in dB scale. Okay, it's a number larger than 1 in that case. So then what I have to do is that I need to cancel this by this negative magnitude here. Okay, I need to cancel that positive magnitude in dB scale by this negative magnitude. Okay, the magnitude of the compensator is 1 over alpha. Okay, at around these frequencies, magnitude of the compensator is 1 over alpha. So if I multiply this with 1 over alpha, what should be the result? Sorry? 0 dB, so in linear scale, 1. So this result should be 1. But this tells you what alpha should be. Okay, what is alpha? It's going to be the magnitude of the system here in linear scale. Okay, that is what alpha is. So alpha is equal to G uncompensated of the system, J omega GC at omega GC. Okay? So alpha is going to be this number. I know that it's going to be something larger than 1. Why? How? Of course, but how can I know that this number is going to be larger than larger? Yes, in dB scale it's already positive. Okay, I know that it's going to be a number larger than 1. Okay. So now, how can I calculate this? I already have a transfer function. Okay. In graphical design, we will only have this body plot in dB scale. So we're going to read this number in dB scale, and then I have to convert it into linear scale. That is all I'm going to do. But here I have the transfer function itself. Okay? And all I have to do is to evaluate the magnitude of that transfer function at this frequency omega GC. Okay? And I calculated omega GC to be 1 over 1.2. So this is going to be 10 over magnitude of j omega is omega 1.2 here. And the magnitude of 1 plus j omega is going to be square root 1 plus 1.2 squared square root. Okay? It's just going to be this magnitude. And if you calculate this is going to be approximately 5. And then we come to the last step 6. So we have so far found K, and the only thing remaining is to find T. Okay? And now what we are going to do in step 6 is the following. It is quite an easy idea actually to understand. So I have find T such that the larger corner frequency of the compensator, which is 1 over T, is 1 decade, at least 1 decade, below omega GC. So what does this mean? So I really want here this negative phase not to affect the phase margin of my system. Okay? So if I select my 1 over T quite close to this gain crossover frequency here, new gain crossover frequency here, then this phase is going to pull my phase down. Okay, so I will lose all of the advantages that are brought by this magnitude decrease. Okay? That means that I'm going to try to place this corner frequency at least 10 times to a lower value than a at least to a value which is 10 times lower than the new gain crossover frequency. Okay? So what that means is that I need to place 1 over T, this frequency where this phase is non-negligible here. Okay, I need to place this at least to a value which is 10 times lower than omega GC. Okay, so I'm going to place it like this. Okay, so what does this mean? This means that 10 over T is omega GC. That means that I put my new gain crossover frequency exactly to this value. Okay, my new gain crossover frequency is exactly at this value, where I am going to be sure that the phase reduction here is smaller than 5 degrees. Okay? So I'm placing my new gain crossover frequency here. So that this reduction here is started, so 1 over T is somewhere here. Okay, so I will place 1 over T at least to a value which is 10 times smaller than this value, which means that 1 over T is going to be somewhere here. Okay? So that actually means the following. I have 1 over T is equal to omega GC is 1.2 divided by 10, which means that T is equal to I have here 100 divided by 12. Okay? So it is approximately 8 here. Okay. That is what T is. So this actually completes the design, and you know what your compensator is. But here I can try to show you what we did at the end. So here, if using this alpha value that we calculated and this T value, if you calculate 1 over alpha T, you get 0.025. And if you calculate 1 over T, it is 0.12. Okay? So then what I can do here is that I can try to place those numbers here. 1 over T is going to be somewhere here. Okay? This is the larger corner frequency of the compensator. And 1 over alpha T is going to be somewhere here. Okay? Let me draw this. And 1 over alpha T is going to be somewhere here, let us say. So what did we do here? We actually reduced the gain of the system so that the new gain crossover frequency is somewhere here. So somewhere on this plot, I have something parallel to this around this place. Okay, and the magnitude change is actually going to start at 1 over T. Okay, so it's going to go parallel until 1 over T. Okay, and then here at this 1 over alpha T, the magnitude of the compensated system should actually match. Okay, this is the compensated system magnitude. Okay, and this one is actually matching this magnitude here, and in between it is going to be deviating from the actual system magnitude. Okay, this red one here is the compensated body plot of the open loop system here. And when I look at the phase of the same thing, I know that the main phase is between 1 over alpha T and 1 over T here. The phase decrease happens somewhere around here. Okay? That is what the phase decrease, where the phase decrease happens. Because it's not around the gain crossover frequency, we are still fine. Right? Any questions? Yes.
10 over T'nin
Omega GC'ye eşitlemek istedik.
Aynen omega GC'ye eşit ve zero görmeyi istedik aslında phase etkisini.
Evet. Ama hala orası zero değil. Yani şurası tam olarak hala zero değil. Tamam mı? Bu faz her zaman negatif. Tamam mı? Negatif ama burası zero olsaydı o zaman o 5 dereceyi eklememe gerek yoktu. Ama şunu hesaplayabilirsiniz. Bu hani şuydu ya, 1 over J omega T, 1 plus J omega alpha T. Bu arkadaşın fazı arc tanjant işte omega t eksi arc tanjant omega alfa t. Tamam mı? Bulduğunuz alfayı buraya koyun, bulduğunuz t'yi buraya koyun, t'leri buraya koyun. Bir de şeyi bulun, 10 bölü t'yi koyun. Buraya yerleştirin. Buradan non-zero bir faz çıkacak, tamam mı? Yani ama negatif bir faz çıkacak. O negatif faz eğer 5 dereceden küçükse magnitude'u you are fine. Ve o 5 dereceden küçük çıkacaktır muhtemelen çünkü şey yaptığımız için. Okay? Okay, so the last thing that I have to mention here is when this thing cannot really work. Consider that we have a plant that we would like to control. Suppose that I have 1 over s squared. Suppose that this is the plant that I would like to control. Instead of the original g of s here, let us say that we have 1 over s squared as our plant. Okay? Let us look at the magnitude and the phase of this thing. And this is the phase. So when I substitute s equals to j omega here, this is going to be 1 over j omega squared. How am I going to draw the magnitude of this thing? At omega is equal to 1, the magnitude is 1. It is 0 dB. Okay? At omega is equal to 1, we have 0 dB magnitude. In other places, how does the magnitude look like? It's going to be a line with 40 dB per decade, minus 40 dB per decade slope. Its magnitude is going to be looking like this. And it's going to pass from 0 dB at frequency 1. This is 10, this is 0.1, etc. What about the phase? It's going to start from minus 180, it's going to end where? It's always minus 180, okay? So the phase is always constant, okay? Now, can I use the phase lag compensator for compensating such a system? No. Why? I can try to reduce the gain. What happens to the phase margin when I reduce the gain? What is the phase margin of the system currently, the closed loop system? It is 0 degrees phase margin. If I decrease the gain a little bit, if I decrease the gain crossover frequency, then what is going to happen to the phase margin? It is always going to remain 0. Reducing the gain is not going to solve any of my problems. The phase margin will not change by reducing the gain. And furthermore, I'm going to add a negative phase coming from the phase lag I will actually make everything worse using phase lag compensator. So how can I compensate such a system? Phase lead compensator. So in this case, the only thing that can work is the phase lead compensator. I need to artificially boost this phase up to around the gain crossover frequency. I need to increase this phase. Okay? So here, do not think that these concepts are quite different from what you have learned in the past. So here, 1 plus. So I have 1 plus Ts, 1 plus alpha Ts. Where are the poles and zeros of this thing? Where is the 0? Minus 1 over t. Where is the pole? Minus 1 over alpha t. In the phase lag compensator, alpha is larger than 1. In the phase lead compensator, alpha is between 0 and 1. Okay? Now, if alpha is larger than 1, what can I say about the pole and zero position? Minus 1 over alpha t is going to have a smaller magnitude if alpha is larger than 1. Okay? So meaning that the pole is here and 0 is here. Okay? And in the other one, I have the reverse situation. Okay? Now this system, open loop system, brings us double poles at the origin. Okay? double poles at the origin. Now I'm claiming that in the phase lag compensator, I will never be able to make the closed loop system stable, but in the phase lead compensator, I will be able to make the closed loop system stable. Okay? And I'm drawing the root locus here. These parts are connected, so these parts are filled here. Okay? How many asymptotes in both root loci here? How many asymptotes would I expect? 2 asymptotes. Where do those asymptotes meet? So here, I'm going to sum the pole position, and then I'm going to subtract the 0 position. Am I going to get a positive number or a negative number? This is -3, this is -5. I will calculate the asymptote intersection point by writing -3 minus 5. Is it going to be positive or negative? It will be positive here. So we're going to get asymptotes here. So these asymptotes, the root locus is going to go there. Can I make the closed loop system stable? No. What is going to change here? What is going to change in this root locus? The asymptote location is going to be in the left half plane. Okay? So I will have this. So I can use phase lead compensator to make the closed loop system stable. I cannot use phase lag compensator anymore. Okay? That's all for that. Thank you very much.